Hello dear friends, welcome to my channel. Today's discussions is quantum field theory. So friends, I have already discussed Mendel's stem variables in my video. Now I want to discuss Yucca potentials. Okay, so let's start. So computed the quantum amplitudes for various scattering processes, but these quantities are a little abstract. We will see how to turn amplitudes into measurable quantities such as cross sections and lifetime unstable particles. So let's start by asking simple questions in classical field theory that will turn out to be relevant. Suppose that we have a fixed del function source for a real scalar field phi that persists for all time. What is the profile of phi x? To answer this, we must solve the static Klein-Gordon equation. That is the lambda square phi plus m square phi equals to del cube x. We can solve this using the Fourier transform and get this equation, and plugging this and use this equation, we get this equation, and changing to polar coordinate and writing k dot x kr cos theta, we have this result. We compute this line integral by closing the contour in the upper half plane. K tends to I infinity, picking up the pole at k equals to plus Im. This gives phi x. The field dies off exponentially quickly at distance 1 by n. The Compton wavelength of the meson. Now we understand the profile of the phi field. What does this have to do with the force between psi particles? We do very similarly calculation to that above the electrostatic, where a charged particle acts as a del function source for the gauge potentials. Lambda square a0 is equal to del cube x, which is solved by a0 is equal to 1 by 4 pi r. The profile for a0 then acts as the potential energy for another charged test particle moving in the background. Can we give the same interpretations to our scalar field? In other words, is there a classical limit of the scalar Euclid theory where the psi particles act as tail function sources for phi, creating this profile? Okay, so phi x is equal to 1 by 4 pi r e to the power minus mr. And if so, this profile then failed as a static potential. The answer is essentially yes, at least in the limit m, capital M, greater than equals greater than m, small m. But the way correct way to describe the potential felt by the psi particles is not to talk about the classical fields at all, but instead work directly the quantum amplitudes. Our strategy is to compare nucleon scattering amplitude to the correct to the corresponding amplitude in non-relativistic quantum mechanics for two particles interacting through a potential. To make a comparison, we should first take the non-relativistic limit. Let's work in the center of the mass frame. P is equal to P1 and is equal to minus P2 and P dash P1 dash. So then friends, we get these equations. Okay, these equations is very known equations. Okay, you have learned it from Feynman diagram. Okay, you know that Mason scattering. This equation you know nucleon meson scattering. So in here I just change the vector. Okay, meson scattering vectors. So this equation I have all you know. If please check, I will give link. You will check that I have already discussed it in my channel. Consider two particles separated by a distance r and interacting through a potential ur. In non-relativistic quantum mechanics, the amplitude for the particle to scatter from momentum states plus minus p into momentum states plus minus p can be computed in perturbation theory. So this expectation is equal to minus I into dq bar ur a to the power a. Okay, so these equations you get, and now their relative factors 2m whole square that arises in comparing the quantum field theory amplitude, and that can be traced the relativistic normalizations, and this is the Kate vector. Okay, so we get this expectations value this equation into these equations. Okay, here we introduced the dimensional parameter lambda is equal to g divided by 2m. We can trivially invert to find this equation, and this equation is exactly Yoka potentials. Okay, so Yoka potential, this is the Yoka potentials. The force has range 1 by m. The Compton wavelength of the exchange particle, the minus signs tell us that the potential is attractive. Notice that quantum field theory has given us an entirely new perspective on the nature of forces between particles, and rather than being a fundamental concept, the force arises from the virtual exchange of other particles. In this case, the meson 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 the Coulomb force arises from quantum field theory due to exchange a virtual photons. Okay, so 5 to the power 4 theory. Now we discuss 5 to the power 4 theory. So important note that the levels of key features, the forces arising due to the exchange of spin one particle such as electromagnetisms, and where the sign flips when we change the charge. However, for forces due to the exchange of the spin two particles. 5 to the power 4 theory. Let's briefly look into the Feynman rules scattering amplitudes for the interactions Hamiltonian H intersection interior equal to lambda divided by 4 factorial into 5 to the power 4. The theory has a single interaction vertex, and which is the factor of minus lambda I lambda, and while the other Feynman rules remain the same. Note that we assign minus I lambda to the vertex I lambda divided by 4 factorial. To see why this, we can look phi phi tends to phi phi scattering, which has its lowest contributions of order lambda with the term minus I lambda p1 p dash is the expectations value. We get any one of the fields can do job annihilations or creation that this gives 4 factorial different contractions and which cancel 1 by 4 factorial sitting out front. Feynman diagrams in 5 to the power 4 theory sometimes come with extra combinatoric factors which is known as a symmetry factors that one must take into account. For more details, see the book The Paskin and Schroeder. Use the Feynman rules, the scattering amplitudes phi to phi, okay, phi to phi tends to phi phi is simply ia equal to minus I lambda, and note that it does not depend on the angle at which the outgoing particles emerge. In 5 to the power 4 theory, the leading other order 2 particle scattering occurs with equal probability all directions. Translating this into potential between two mesos, we have these equations and connected diagrams, and this is my symmetry, okay, and connected diagram and amplitude diagram. So we have seen how one compute amplitudes by writing down all Feynman diagrams and assigning mean integral to them using the Feynman roots. In fact, there are a couple of a caveats about the Feynman diagram. You should write down. Both of these caveats are related to the assumption we made earlier. The initial and final states are eigenstates of the free theory, which, as we mentioned at the time, is not strictly accurate. The two caveat which go some way towards ameliorating the problem the following. We consider only connected Feynman diagrams where every part of the diagram is connected to at least one external line. We shall see shortly this will be the related to the fact of the vacuum car vacuum Kate 0 of the free theory is not the true vacuum Kate omega interacting theory. An example of diagram that is not connected is this is my connected diagram and this is my unamputated diagrams. What we measure cross sections decay rates. So far we have learned to compute the quantum amplitudes for particles decaying or scattering as usual quantum theory. The probabilities for things to happened are the modulus square quantum amplitudes. In these sections we will compute these probabilities known as decay rates cross sections. One small subtly tilty here is that S matrix elements, this is the expectations if S minus 1 I all come with a factor of 2 pi to the power 4 and del to the power 4 pv minus pi. So we end up with the square of the delta functions, and as we will now see This comes from the fact that we are working in finite space. So friends, Fermi golden rule. Let's start with something familiar and recall how to derive Fermi golden rule from Dyson's formula. For two energy eigenstates Ket m and Ket n, with Em does not equals to En, we have to leading order in the integration. This expectation value is this value, and we get minus I into m, this expectation, integration 0 to 2 dt dash ei omega t dash, and after math this we get this value, where omega equals to em minus en. This gives us probability for the transition from eigenspace ket n to ket m in time t as p n tends to m t is equal to this value. The function is brackets in plotted in figure. This figure we will show figure 19. For fixed t, we see that in time t most transitions happen in a region between energy and eigenstates separated by del E is equals to 2 pi divided by t. As t tends to infinity, the function in the figure starts to approach a delta function. To find the normalization, we can calculate d omega is equal to pi t del omega as t tends to infinity. Consider the new transitions to cluster of states with density rho e. In the limit t tends to infinity, we get transitions probability. Okay. So transitions probability, this is my transition probability, and we get which gives a constant probability for the transitions per unit time of the states around the same state and a same energy state En proportional to Em. And Fermi golden rule. In the above derivation, we are familiar careful with taking the limit as t tends to infinity. Suppose we were a little sloppier and first close to compute the amplitude for the state ket n and t tends to minus infinity transition state ket m at t tends to plus infinity, then we get this equation. And now when squaring the amplitude to get the probability, we run into the problem of the square of delta function p n tends to m. This is this value we get. Okay, tracking through the previous computation, we realize the extra infinity is coming because p m tends to n is the probability for transitions. Probability for the transitions happen in infinite term. Happen infinite time t tends to infinity. We can write the delta functions. Okay, so 2 pi square del omega square is equal to 2 pi del omega t. Okay friends, so final states Fermi golden rule. Okay, now we discuss that Fermi golden rule. We have exchanged one of the delta function. So Lorentz invariant measures, the result is an expression for the density final states given by Lorentz invariant measures. The second step is the sum over all final states with different numbers and possibly of particles. This gives us our final expression for the decay probability per unit. Gamma is equal to P, and gamma is equal to this integration summation, and gamma is called the width of the particle. It is equal to reciprocal of the half life t tau is equal to 1 by gamma. Cross sections collide two beams of particles. Sometimes the particle will hit the bounds of each is called the cross section, is denoted by sigma. The fraction of the time that they collide is called cross section, is denoted by sigma. If the incoming flux F is defined to be the number of incoming particles per area per unit time, then the total number of scattering events capital N per unit time is given by N is equal to F sigma. We would like to calculate sigma from the quantum field theory. In fact, we can calculate a more sensitive quantity d sigma known as the differential cross section, which is the probability for a given scattering processes to occur in the solid angle theta comma phi. More precisely, d sigma is equal to differential probability unit time unit flux, where we have, and we get this value result, where we have used the expression for probability per unit time that we computed in the previous subsection. U1 E2 are the energies of the incoming particles. We now need to expression for the unit flux. For simplicity, let's sit in the center of mass frame of the collision. We have been considering just a single particle spatial volume V, meaning that the flux is a given term is three velocities vi as a v mod of vi v1 minus v2 divided by v. This then gives d sigma is equal to 4 by u1 e2 1 by v1 v2 is equal to this equation. If you want to write this in the term of the momentum, then recall from your course on special relativity that the three velocities vi are related. The momentum v is equal to p divided by m into root over 1 minus v square equals to p divided by p0. So in this equation, d sigma equation is our final expression relating the S matrix to the differential cross sections. You may now take your favorite scattering amplitude and compute the probability for particles to fly out at your favorite angles. This will involve doing the integral over the phase pair of final states with measure d capital pi, and notice that the different scattering amplitude have different momentum dependence and will result in different angular level. Scattering was simply a is equal to minus lambda, and this result in isotropic scattering. In contrast, for nucleon and nucleon to nucleon scattering, and we have schematically a proportional to t minus m square whole inverse plus u minus m square whole inverse. This gives rise to angular dependence in the differential cross section, which flows from the fact that, for example, t is equal to minus 2p 2 mod p whole square 1 minus cos theta, where theta is the angle between the incoming outgoing particles. Green functions. So far we have learned compute scattering amplitude, and these are nice physical. They are directly related to cross sections and decay rates, which are physical. But there are many questions we want to ask quantum field theory that are directly related, that are not directly related to scattering experiment. For example, we might want to compute the viscosity of the quark gluon plasma, or optical conductivity in a tentative model of strange metals, or figure out the non-Gaussianity of density perturbations arising in the CMB from Lovell model of inflation. All of these questions are answered in the framework of quantum field theory by computing elementary objects known as correlation functions. In this section, we will briefly define correlation functions, explain how to compute them using Feynman diagrams, then relate them back to scattering amplitudes. We will leave the relationship to other physical phenomena to other courses. We will denote the true vacuum of the interacting theory as kate omega. We will normalize H such that H of kate omega is equal to 0. But the last term vanishes. This follows the Riemann-Lebesgue lemma. Riemann-Lebesgue lemma gives us this t dash limit t tends to infinity probability, this probability value, this probability value. So we get these equations. We now apply the formula and we get this equation. Connected diagrams and vacuum. Now we discuss connected diagram, and omega to omega gives us the left hand side. Okay, connected diagrams and vacuum bubbles, that we getting closer to our goal, computing the green functions gn, since we can compute the probability value, and this is used the methods of S matrix elements, and namely Dyson's formula and Week's theorem, Feynman diagrams. But what about diving one by other? What's that's all about? Okay, then we have diagrammatic expansion, probability 0 is 0. So this is the diagrammatic expansion. These diagrams are called vacuum bubbles. The combinatoric factors and associated with each diagrams are such that whole series sums, and omega 1 equals to 1, and we get these equations. This is our green function, and green functions lets the phi h and phi and the gn is the correct correlations of the functions, and we prove the following results. Okay, we don't need to prove and claim Heisenberg pictures phi